When we're training an AI, we need a way to measure exactly how far off its predictions are, and more importantly, exactly how to nudge our numbers to fix those mistakes. In PyTorch, the engine that handles this improvement process automatically is called Autograd. To understand how it works, we have to look back at tensors, those raw data blocks we covered in the last episode. They hold all the numbers our AI uses to think. For an AI to actually learn, these data blocks can't be static. They need a memory system that records every single math operation performed on them as they move through the network. This memory system is what allows a collection of numbers to become a self-correcting foundation for artificial intelligence. We turn this memory on using the command requires grad equals true. Think of this as flipping a physical ignition switch that tells PyTorch to start paying attention to a specific tensor. Once that switch is flipped, PyTorch begins tracking every single addition, multiplication, or transformation that happens to that data. This line is the absolute starting point for the machine to learn from its errors. If we don't track these changes, the AI will be completely blind to its own mistakes and have no idea how to adjust itself to do better next time. When we perform our normal math, multiplying inputs by weights to get a result, we call that the forward pass. This diagram shows what's happening behind the scenes. PyTorch silently builds a map of the entire journey, a computational graph. Every math operation creates a new node, which remembers exactly what function created it, forming a linked chain of events. The forward pass isn't just about getting an answer. It's about leaving behind a permanent, step-by-step blueprint of exactly how that answer was reached. This comparison shows why the blueprint is important. Calculating how much each tiny step contributed to a final mistake is a math nightmare. Doing it by hand using the chain rule, seen on the left, is exhausting and very easy to get wrong. PyTorch solves this with a single magic line of code, loss.backward. This diagram shows that command in action. It triggers a total U-turn, walking backward through the blueprint we just built to figure out the math automatically. By tracing the path in reverse, PyTorch calculates the precise amount of blame to assign to each starting number for the final error. This command handles all the complex calculus for us, letting us optimize even the most massive networks with just one line of code. But there is one major trap to watch out for. By default, Autograd doesn't overwrite the old results when it calculates these values. It adds them together. If you run a second calculation without resetting, the new values will stack on top of the old ones. This creates heavily inflated, incorrect numbers that can ruin your training. To fix this, we have to call a command named .0.s before every new training step. Think of it like opening the flush valve on this beaker to wipe the slate clean. If you don't clear these out, the AI will learn using a corrupted history, making adjustments based on old, compounded mistakes. We don't always want PyTorch tracking our math, especially when we're just testing a finished model or manually updating our weights. This table shows the different ways to go off grid. The most common way is using a with_torch.no_grad block, which temporarily cuts the tracking tether. Disabling tracking in these moments is a vital step. It saves a massive amount of computer memory and keeps the system from recording things it doesn't need to. Now that we see the individual gears, let's look at how they form the universal cycle used to train almost every modern AI. This cycle is the heartbeat of learning. It starts with the forward pass to get a prediction, immediately followed by calculating the loss. Then we use the backward pass to calculate adjustments, update weights, and zero out the results to start fresh. Build the map, walk it backward, update the numbers, and reset. This 5-step rhythm is the foundation of how PyTorch models learn to think. In our next episode, we're going to take this Autograd engine and use it to construct your very first fully functional neural network from scratch. Now that you know how the engine works, you're finally ready to build the whole machine.